Hello and welcome to lecture number 7 in the course Advanced Robotics. In the last class, I had explained how to assign the DH parameter table for the Puma robot and then how to find the forward kinematics equation. We had also said that the forward kinematics is given the joint angles and the link parameters, how you can find the position and orientation of the end effector. Today we'll move on from there and then we'll cover the topic of inverse kinematics, which is more important in the sense that when a robot has to do a task, it has to actually go to a particular point and pick up an object or do a task. So it has to go to a point with a given position and orientation of the end effector. And for that corresponding position and orientation of the end effector, we have to find what is the corresponding joint angles, and that is the inverse kinematics problem. So today we'll start off by looking at the inverse kinematics of a 3 degree of freedom system, and then we'll look at the inverse kinematics of the Puma robot. We'll also consider the concept of solvability. When can you solve such a system of equations, and why is it difficult to solve the inverse kinematics of many manipulator systems? Okay, so today let's very quickly revise what we had done in the last class about forward kinematics and then move on to the inverse kinematics problem. So the example I had given in the last class was for a 3 degree of freedom system. We can very quickly revise. So it has 3 degrees of freedom planar manipulator system where we have 3 joints which are like this. So the first thing that we do is we assign so this is a 3 degree of freedom robotic mechanism, and it is planar. So please note that it cannot come out of the plane. It is on the plane and on the z-axis are pointing outward. So we assign our DH parameters and assign our z-axis this way. So z-axis is pointing out of the plane as it is rotating about this axis. So this is z0, z1, z2, and this is my z3. Then I assign my x-axis as x0, x1, x2, and x3. Okay, so this is my 3 axis of the 3 x-axis. Then we make our DH parameter table, which I had done in the previous lecture, and my DH table will be A alpha, D, and theta, which will come out like this. This is my joints 1, 2, and 3, and this is 0, 0, 0, theta 1. This is L1. So this is my link length L1. This is my link length L2, 0, 0, theta 2, and this is L3, 0, 0, theta 3. Then what we do, we take the generalized matrix. We take each row of the DH table and put it inside the generalized matrix and get the corresponding matrices which relate one frame to the previous frame. So in this case, if I want to relate the third frame, the origin of which is given here, to the 0 frame, then what I'll be doing is I'll be finding 0 to 1 multiply with 1 to 2 and then 2 to 3. Okay, this gives us so this matrix will give us the position and orientation of the third frame with reference to the 0 frame. Okay, now when I put in the matrices, please refer to the previous notes what the matrices look like. Okay, so the matrix will look like T01, which is equal to, sorry, let me write the full matrix. Okay, T01, which is equal to cos 1 minus sin 1 cos 1, 0, 0, 1, 0, 0. Sorry, it's a 4x4 matrix, so this is 0, 0, 0, 1. This is 0, 0, 0. So the second matrix will be 1 to 2, which is equal to cos 2 minus sin 2 cos 2, 0, 0, 1, 0, 0, 0, 0, 0, L1, 0, 0, 1. The third one, 2 to 3, will be equal to this is cos 3 minus sin 3 cos 3, 0, 0, 1, 0, 0. This is 0, 0, 0, and that is L2, 0, 0, 1. Now when I multiply them all out, then what we'll be getting, this matrix T0 to 3 would to be equal to cos 1, 2, 3 minus sin 1, 2, 3 sin 1, 2, 3 cos 1, 2, 3, 0, 0, 1, 0, 0. This is L1 cos 1 plus L2 cos 1, 2. This is L1 sin 1 plus L2 sin 1, 2. This is 0. This is 0, 0, 0, 1. Okay. Now in this matrix, this relates the third frame with respect to the 0 frame. Okay. Now please note that this has 4 parts. This part is the translation of what? This is the origin of the frame 3. Okay, so the distance it has moved in the x direction is my x. So this will be x, so this is my x. On the y-axis, this is going to be my y. Okay, this is my y. Okay, so this is my y, and the z direction is 0. So my x, y, 0, what do they mean? They basically mean this is equal to x, y, and 0. So x, y, 0 is the code, x, y, and z is the coordinate of this point with respect to the base frame, which is given by x, y, and it doesn't move in the z direction, so z is equal to 0. Okay, so this is the meaning of the position of the end effector, or position of frame 3 in this case. And what is the orientation? This is the orientation. Okay, that is the orientation. Now what is the orientation? Orientation is this angle. If this is my x3, then x0 was in this direction, right? So x0 is this side and x3 is in that side. That's x3. So this angle, if I call it phi, okay, then that is my orientation, which is given by this matrix. Okay, so my x0 is here and x3 is there, so the orientation is given by that. Okay, so now the forward kinematics problem would be that I know that x, y, and z is 0, so I'll simply write x and y only. So in my forward kinematics problem, we are writing x is equal to L1 cos 1 plus L2 cos 1 2, and y is equal to L1 sin 1 plus L2 sin 1 2, and phi, the angle, is equal to theta 1 plus theta 2 plus theta 3. Okay, now this one, because it is planar. Okay, now in the forward kinematics problem, so let's call it the FK problem, the forward kinematics, my input is thetas. Okay, and L1, L2 is known. Okay, let's say, for example, theta 1 is equal to theta 2 is equal to theta 3 is equal to 30 degrees, and L1 and L2 is equal to 1 unit. Okay, in that case, x is equal to 1 into cos 30 plus cos 60, and y is equal to sin 30 plus sin 60. Okay, so which is equal to 1.36, and this is also equal to 1.36. And what is phi? Phi is equal to 30 plus 30 plus 30, which is equal to 90. So this is my forward kinematics problem. Now suppose this is forward kinematics, so this is 1.36, 1.36, that's my x, y, and z is 0, and this is my phi. Now suppose I give you this as input, I give you this as input, and I say that you find this. Okay, so this is given, and find this one now. That means I'm giving you x and y equal to 1.36, 1.36, phi is equal to 90 degrees. Now you tell me what is the corresponding theta 1, theta 2, and theta 3. So find, so given x is equal to 1.36, y is equal to 1.36, and phi is equal to 90, find theta 1, theta 2, theta 3. That is what is called the inverse kinematics problem. Now this is more important for us because when you look at a normal robotic system, okay, suppose I want to go and pick up this object here, which is maybe on a table, then I have to go to this point P, and I'm giving you the x, y, and z, and alpha, beta, gamma, okay, which are the three angles of the end effector at when it goes to pick it up like that. Okay, so now I'm giving you this, and I now say you find out what are the corresponding thetas. So from the control point of view, the inverse kinematics is more important than the forward kinematics, and it's more difficult also. Okay, so given, so what is the definition of inverse kinematics? Given given x, y, z, and alpha, beta, gamma, find thetas, the corresponding joint angles. In the case where there is a prismatic joint, it can be thetas or it can be d when there is a translating joint. Okay, now let's go back and say that given, what does that mean? So it basically means in this figure, suppose I give you this x, y, z, and alpha, beta, gamma. Okay, now given means what? Given means if I write the given, so it will become cos phi minus sin phi cos phi 0 0 1 0 0. This is 0 0 0 0, and this is my, let's call it x, y, and z 1. Okay, and what are the values of x, y, and z? We have seen that values of x, y, and z, these are numerical values, right? So these values are going to be the numerical values. So x, y, and phi. So the matrix there, let's call it T given, is equal to cos 90 minus sin 90 cos 90 0 0 1 0 0. This is 1.36 1.36. This is 0. That's 0 0 0 1. Okay, in terms of variables, this would be written as cos phi okay, minus sin phi cos phi, okay, 0 0 1 0 0 0 0 0, and here it is x y z and 1. Okay, so this is my t given. This is the numerical value which will be given. So what do we do by given? Means this is given now, so this is my t given. So I equate this to this now. I equate this matrix to this matrix. Okay, and then we have to try and solve term by term. What does this mean? This means that I equate, for example, I equate this term with this term. Cos phi is equal to cos 1 2 3. Okay, so if I write it in full, you'll appreciate it better. Cos theta 1 plus theta 2 plus theta 3. Now from here you cannot solve anything. It's like saying 90 cos 90 is equal to cos of theta 1 plus theta 2 plus theta 3. Now from here you cannot do anything, you cannot solve anything. And these are basically what are called transcendental equations. You can see that there is sine and cos in all kinds of terms. When we looked at the Puma robot in the last class, we saw that it has 6 degrees of freedom, and when you do the forward kinematics, you find out each of these terms. You find that the corresponding x, y, z and the rotation matrix, these terms, they contain all combinations of sine and cos. Okay, so it's very, very difficult to solve, if not impossible to solve. Now this is what makes the solution procedure of a system very, very difficult. So let's look here a little bit more in detail. So what we're trying to solve is this system of equations. So what we're trying to solve is cos phi minus sin phi cos phi 0 0 1 0 0 0 0 0, and this is x y z and 1. Okay, and the right hand side, for the Puma robot you have r11 r12 r13 and px py pz and 1. So r21 r22 r23, and here you have r31 r32 r33 0 0 1. Okay, now we are trying to solve this system of equations. So solving the kinematic equation is a nonlinear one. Okay, so this equation is nonlinear and transcendental equations. Okay, now the kinematic equations are nonlinear and they are transcendental equations. Now if you can solve this set of equations, then we say they are solvable. Now if you cannot solve, then they're not solvable, right? Now let's look at this with the example of the Puma robot. Okay, so we talked about the Puma robot, which had 6 degrees of freedom, because that means there are 6 thetas. So we have theta 1 to theta 6. Okay, and we saw that this final matrix comes out in all different terms. Okay, now how many equations are there? So total number of equations is equal to 4 by 4, which is equal to 16. And how many variables are there? In the case of the Puma, there are 6 variables. Okay, so it would appear that there are 16 equations and 6 variables, so it should be very easy to solve because there are more number of equations than variables. But if you look very carefully at the two sides of these two matrices, what you see is that this set of terms, which is 4 here and 4 there, these are basically trivial solutions. Okay, what is the meaning of trivial solutions? Trivial solution means 0 is equal to 0, for example. It doesn't mean anything. 1 is equal to 1. You can't solve anything from there. Okay, now so these are useless for us. So it doesn't mean that there are 16 equations. Actually there are actually 12 equations. Now in this 12 equations and 6 variables, still it may be difficult to solve. Okay, now the first condition that is required for solving the first condition for solving is end effector inside workspace. That means the robot, let me give this example, very simple example. Okay, it has to be inside the workspace. So this position orientation should be inside the workspace. Obviously, if I give a point there, it cannot go there. So it is outside the workspace. So the first condition is that it should be inside the workspace. Now inside workspace also there are two workspaces. So inside workspace, number one is what we call a dexterous workspace. What is the dexterous workspace? The end effector, let's call it the end effector EE. So I'm writing in short, the end effector can reach in all orientations. Okay, that means if I take a point here, or if I take a point here, for example, the manipulator can go like this, it can come like this, it can come like this, it can go like this. Okay, that means the end effector can reach this point in all orientations. That we call this as the dexterous workspace. And there's the second one, which is called the reachable workspace. Now what is the reachable workspace? Reachable workspace means it can reach, okay, so end effector reach in at least one orientation. And where would this be? For example, you can imagine if it is stretched, if the arm is stretched out like this, then here it can go only like this. It can't go from this side, neither can it go from this side. Okay, so here there is only one solution. So this is my reachable workspace. Okay, so there are two workspaces, dexterous workspace and reachable workspace. Now this would mean how many solutions are there? How to decide whether you're on dexterous workspace or reachable workspace? So if your system is solvable, okay, that means solutions exist. Then the question is how many solutions? Okay, and how many solutions would mean if you are having multiple solutions, then if you're having very large number of solutions where you can go in all orientations, then it is that solution is in the dexterous workspace. Whereas if you are in the reachable workspace, you'll get maybe just one solution. So obviously you understand that if you're somewhere in the outer ranges, you'll just be getting one solution. Whereas in the case of, for example, the Puma robot, so let's look at the Puma robot here. So this was the Puma robot, which I had done it in the last class. We'll look at it in this class again. Okay, so this is the Puma robot. Okay. So this is it has 6 degrees of freedom, 6 thetas. So if I draw the side view of this, let's consider only this as a two-link manipulator. Okay. Now the dexterous workspace would be somewhere in this region. The outer spaces are going to be the reachable workspace, and here is going to be the dexterous workspace. That it may be able to go in all configurations somewhere here. Okay, it can go in all configurations. That would mean that it has a large number of solutions here, whereas here in this region, when it is fully stretched, it may only have one solution. Okay, so the number of solutions also depend on where you are in your workspace. Okay, so we have seen solvability, of course. Solvability means solutions exist, and depending on how many exist, you are either in your dexterous workspace or you're in your reachable workspace. Okay, so we saw a couple of terms: dexterous workspace, reachable workspace, and next we'll talk about these the type of solution. For example, the other point here is that we need to note very carefully is the concept of multiple solutions. Why multiple solutions? Now this is very easy to understand. Let's see a two-link manipulator like this and like this. It is at this point. Okay, now this is one solution. There can be another solution which is that side. Why two solutions? Because the sine and cos terms have two terms. Okay, two solutions always. What I mean is sine 90 and sine 270 will have the same value, okay, which is equal to 1. Similarly, cos 0 and cos 180 will both be 0. That means in terms of solutions, if we say cos theta equal to 0, you actually have two solutions there. So because these are all sine and cos terms which are going around, and there are 6 of them in the case of the Puma, so you'll have multiple solutions. Similarly, in the case of the 2 degree of freedom system, this is an example of 2 solutions. Okay, and this is something that also makes the solution procedure tricky. Now, when we're talking about solutions, when we are trying to solve, okay, we talk about a closed form solution. So if a solution exists, or rather, let's say the way of solving, we can have a closed form solution. Now, closed form solution basically means using an algorithm which uses algebraic or geometric method to get all solutions. Okay, so closed form solution means an algorithm which uses geometric or algebraic methods to get all the solutions. So if you get all the solutions, then we say this is a closed form solution. What's a numerical solution? So a numerical solution is one in which is basically an iterative method, in which used an iterative method, and these are also approximate, and so you use iterative method and get approximate solution. Okay, so in robotics we do not use numerical methods because you don't get exact solutions, you get iterative solutions. Okay, and you get approximate solutions, which we don't want in robotics. Why? Because if there is even a very small error, then what is going to happen is you might end up with a robot is going to operate for millions of cycles. So if you're operating with even a very small error, say 0.1 millimeter, if you're multiplying that with millions and millions of cycles, it will suddenly become a very large error. Okay, so we do not use numerical solutions in robotics, and we use only closed form solutions. Okay, so now let's go back and revisit the inverse kinematics problem, the way the problem is stated. So the way the problem is stated is you are given the desired position and orientation. So this is T desired, and this is T. This is my Tn to T0. That means the end effector. Let's call it the end effector to the 0 solution. So let's take this example of the 2 degree of freedom manipulator and start off. Okay, so here let's see, write down the 2 degree of freedom manipulator example here. Let's see, let's call it, let's make it 3 degrees of freedom. Yeah, that. Okay, so 3 degrees of freedom. So 3 DOF, 3R degrees of freedom. Now I have already written down the matrix. I've assigned the frames and all that. So Z0, Z1, Z2, Z3. This is X0, X1, X2, X3. Okay, and this is my L1, L2, L3, and this is my theta1, theta2, and theta3 is there. So let's say that my T desired is equal to T3 to 0. Equate them. Okay, then try and solve. Or T desired and T given. The desired has to be given. So let me write down the desired is cos phi minus sin phi, cos phi, 0, 0, 1, 0, 0. This is 0, 0, 0. And this is my x, y, 0, 1. Which is equal to, the other side we have cos 1, 2, 3 minus sin 1, 2, 3, 0, L1 cos 1 plus L2 cos 1, 2. Then it is cos sin 1, 2, 3, cos sin cos 1, 2, 3, 0. This is L1 sin 1 plus L2 sin 1, 2. This is 0, 0, 1, 0. This is 0, 0, 0, and 1. Okay. So now I hope, yeah. So please note that this is L1 cos 1 plus L2 cos 1, 2. Okay. This is one full term. This one full term. Okay. Now As I said that we have to equate equations term by term and see how we can solve. Now if you start equating from this side, if you start equating from here, cos phi and cos 1, 2, 3, if you do it like this, cos phi is equal to cos 1, 2, 3, then you cannot find, you will not be able to solve. Okay, this has no meaning, you cannot do anything with this. Similarly, if you say sine phi is equal to cos sine 1, 2, 3, again you will not be able to solve. Okay, so sine phi is equal to sine 1, 2, 3. These are not, you cannot solve for theta 1, theta 2, theta 3. Okay, so one way of trying to solve is, let us target the position first. Okay, so I target this and equate this with the, let me use some other color. So this I'm equating with this, and this term I'm equating with this term. Okay, now why did I do that? Because if you see on the left hand side, equating this with this doesn't mean anything. 0 is equal to 0, again 1 is equal to 1, it doesn't mean anything. So there are 16 terms, actually there are 16 equations, but a majority of those equations are trivial, so there's no point, there's nothing you can do with them. So the only ones that are making sense are this one, this 4 terms here and these 2 terms here. So there are actually 6 terms only, 6 equations which make some sense. Now out of which, if you start targeting cos 1, 2, 3, you'll not be able to solve. So let's target the other side, L1 cos 1, and see if we can solve this system of equations. So L1, so let us say x is equal to L1 cos 1 plus L2 cos 1, 2, and y is equal to L1 sine 1 plus L2 sine 1, 2 plus L2 sine 1, 2. Okay, now here we see that there are two variables, theta 1 and theta 2. Okay, they have sine and cos terms, but we know the sine squared plus cos squared is equal to 1. So can we make use of that? So these are two equations. Let's call it equation 1 and equation 2. So here we can say that squaring and adding, okay, this 1 and 2, we get x squared plus y squared is equal to L1 squared cos 1 squared plus L2 squared cos 1, 2 squared plus twice L1 L2 cos 1 cos 1, 2. That's the first equation. The second equation will be plus, okay, let me write it just below, plus L1 sine 1 squared plus L2 squared sine 1, 2 squared plus twice L1 L2 sine 1 sine 1, 2. Now let us add them. Okay, once you add them, what you get, x squared plus y squared is equal to, so we have cos 1 squared plus sine 1 squared. I can take L1 squared common, so L1 squared, I take it common, we get cos 1 squared plus sine 1 squared, okay, plus L2 squared is equal to cos 1, 2 squared plus sine 1, 2 squared, okay, plus twice L1 L2. So we have cos 1 cos 1, 2 plus sine 1 sine 1, 2. Okay, now this term will become equal to 1. So this is equal to 1, this is equal to 1. So we get L1 squared and L2 squared. Here we get cos theta 1 plus theta 2 minus theta 1. Okay, so theta 1 and theta, this will cancel. So you get cos 2 here, equal to cos 2 here for this term. Okay, so what we get, L1 squared plus L2 squared plus twice L1 L2 into cos 2. So theta 1 is gone. Okay, so let me write this equation again. Simplifying it, what we got here is x squared plus y squared is equal to L1 squared plus L2 squared plus twice L1 L2 cos 2. This is what we have got. So theta 1 got cancelled out. Okay, so this is something interesting. We were able to solve because that happened. Now if that did not happen, then you would not be able to solve. Okay, so now what we find is cos 2, let me write cos 2 is equal to, so I take this 2 on this side, so cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. Okay, now here please note that there is a warning here, do not take cos inverse. Okay, cos inverse. Why? Because there are always two solutions. Now you might think, so what if there are two solutions? Now what are these two solutions? This is one solution. Okay, this is one solution. Okay, let's say this is one solution. Okay, so theta 1 and this is my theta 2. That's one solution. Now what is the other solution? The other solution is on this side. Okay, so this is theta 1 dashed, that's my x and that's my y, and this is minus theta 2. Okay, so solutions will come in pairs. What do I mean? This solution 1, if I call this solution 1 and I call this solution 2, then solution 1 has theta 1 and theta 2. The second pair has theta 1 dashed and minus theta 2. Okay. Now you cannot cross the solutions, which means that you cannot cross. What is the meaning of cross? Cross solutions, which means that you cannot take theta 1 and minus theta 2. Okay, and similarly you cannot take theta 1 dashed and theta 2. Okay, this is incorrect. So this basically means that one of the links is here, okay, and the other link is there. Okay, this is the meaning of minus theta 2 and this is the meaning of theta 1. So if I take this solution, this is what it means. There is no connection here. Now is this a correct solution? Yes. In terms of mathematics it is correct, because why? Cos of minus theta is equal to cos theta. Okay, so as far as this cos of minus theta and plus theta is considered, they are the same, but physically it doesn't make any sense because there is no connection here. Okay, so no connect. Now a computer program or an algorithm which is running this, if you're writing a computer program to perform this task, to do this computation, then what is going to happen is the computer program will not be able to make out this difference. And what it can do, it can by mistake, it can take this one and it can take that one. Okay, what will happen in the real manipulator, it will end up with this situation. Now the program obviously cannot see, so although it is a mistake, the computer will not know that a mistake has been made. Okay, so what we do is, from cos 2, we have got cos 2 is equal to, now we have just seen cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. Okay, so from here we take sine 2, which is equal to root over 1 minus cos 2 squared. Okay, we convert this to sine 2. Then we use the function theta 2 is equal to a tan 2 sine 2 and cos 2. Now this is a special function which takes only the positive values of sine and cos. Okay, and then finds theta 2. Okay, so it took only the positive sine and took the positive cos. So what it did is essentially took this one, took this one and this one, both are positive. Now once you get the solution, what is the other solution? The other solution is theta 1 dash and minus theta 2. Okay, so once here I have got this as one solution, so one solution is theta 2. The other solution is, what is the other solution? It's minus theta 2. Okay, so for example, if this is 30 degrees, this will simply become minus 30 degrees. Okay, but we have to take the use the function a tan 2. Okay, not tan inverse, otherwise this problem is there. So what can happen is you might end up with one being positive and the other being negative, and they are not in pairs. Okay, we have found theta 2, the solution theta 2. Now what we need to do is we need to find the solution theta 1. Okay. Now we can find the solution in different ways. We can use algebraic methods, we can use geometric methods in solving this. Okay. Let us use geometric methods and try and solve for theta 1. So we are going to use the law of cosines. So we're going to use the law of cosines and derive the solution. So let me look at it this way. Let us try to understand it this way. This is my x-axis and my y-axis, and here we have okay, that is the two-link manipulator. This was my point xy. Okay, now let us do this construction, this very simple construction. So this is one solution, that's the other solution. Okay, so this is my theta 1. Let me call this theta 1. This is the angle theta 2 which we have found. Theta 2 obtained. Okay, so we want to find theta 1 now. Theta 1 we need to find. So let us do this this is my theta 1. So let us write down this. This is the angle beta and this is the angle psi. Okay. Now from here we have got our angle beta and angle psi. Now what is angle theta 1? Theta 1 is equal to beta minus psi. What is theta 1? Theta 1 will be equal to beta plus minus psi, plus or minus depending on whether it is this side or it's on this side. Okay. Now let us look at the law of cosines. So here beta is equal to, what is the angle? Beta is equal to a tan. Beta is this angle, so a tan xy is the coordinate of this point, so it is this side by that side. So this is my y, that's my x. So y by x. Okay, so let me write it a tan y by x. So I've got the angle beta. Okay, now using law of cosines, cos of psi is equal to x squared plus y squared plus L1 squared minus L2 squared divided by 2L1 root over x squared plus y squared. Okay, so we have got cos psi now. Okay, so now theta 1 is equal to beta plus minus psi, depending on if theta 2 is less than 0, then we take plus, and if theta 2 is greater than 0, we take minus for psi. Okay, so this plus minus is that. So having got cos psi, you can get psi from there. Okay, so this is a geometrical method of getting the solution of theta 1 and theta 2. There is another way of solving. Let us look at the other way of solving. So this, I'm going to draw the same manipulator system here. So it's a so let me draw this, my x-axis, that's my y-axis. Then let me draw the two-link manipulator again. This is my 1 degree of freedom, this 2 degree of freedom, it is here. This is my point xy. Okay, I make this very small construction. So this is my construction. Okay, this is my angle theta. This is my angle theta 1. This is my angle theta 2. Theta 2 and theta 1 are there. There are again two solutions. One solution is here and the other solution is on the other side. Okay, now let me define, like in the previous case, let me define these two angles. So let me call this alpha. This full angle is alpha, and let me call the other fellow beta. This angle is beta. Okay, now for beta, let me make a bigger triangle. Okay, and the link lengths are L1 and L2. So link lengths in the previous case also I forgot to write down, this is L1, that's L2. Now here also, this is my L1, this is my L2. Okay, so what is alpha? Tan alpha is equal to y by x. Okay, so this is a projection here, so that's x, and that on the other side, on the y side, is y. So tan alpha is y by x. Okay, that's what we get from the big triangle. Now what is tan beta? Tan beta, so beta is here. So if you look at this triangle which is drawn with the light blue color, then it is this length by that length. So tan beta is equal to, so this is equal to L2 sine 2, and this is L2 cos 2. Okay, so which is equal to L2 sine 2 divided by L1 plus L2 cos 2. Okay, so we have got tan alpha and tan beta. Now we can use the formula tan alpha minus beta is equal to tan alpha minus tan beta divided by 1 plus tan alpha tan beta. Okay, Now we can, so we have got tan alpha minus beta, so theta 1 is equal to a tan 2 alpha minus beta. Okay, so we have got our theta 1 here. So we had got theta 2. Theta 2 is known. Okay, we had got theta 2 earlier, so I can find theta 1 like this. So this basically gives us a method of, I've shown two methods, geometrical methods for finding theta 1 and theta 2. Okay, now once you have got that, what is phi? What is the angle? So we have seen that either we can equate cos phi is equal to cos 1, 2, 3, or sin phi is equal to sin 1, 2, 3. That is, I go back to this equation, what is given. So what was given is this. So I take this, equate with that, take this, equate with this, and we have already known. So what is known is theta 1 and theta 2, right? So theta 1 and theta 2. So theta 1, theta 2 are known. Okay, find theta 3 now. Okay, so we can use these two equations and then try and find, or in the planar manipulator, phi is equal to theta 1 plus theta 2 plus theta 3. Okay, so from here we can straight away get the value of theta 3. We can straight away get theta 3 from there. Okay, so from here I can get this taking cos inverse, and then I can simply get the value of theta 3 here. Okay, so as a numerical example, which I gave some time back, t desired, t given or desired could be equal to cos 1, 2, 3. Okay, so cos 90 minus sin 90, sin 90, cos 90. Okay, so 0, 0, 1, 0, 0. This is 1.36, 1.36, 0, 0, 0, 0, 1. And now you find theta 1, theta 2, theta 3. Okay, so we should be able to get the solutions for theta 1, theta 2, and theta 3. This will of course be, and this will be 0, that will be minus 1. This is going to be 0, that will be 1. Okay, so this is showing the inverse kinematic solution of this problem. Now let's go back to the bigger problem. We're talking about the problem of the Puma manipulator. The problem of the Puma manipulator. And we had done the forward kinematics in the previous class. Please have a look at those lecture and the slides there. So what we had done is we had assigned your DH parameter table. So we made our A alpha d theta table, and from that A alpha d theta table, 1, 2, 3, 4, 5, 6, we had made our transformation matrices. Okay, so this is my Z0, Z1 axis. This is Z2, Z3 is there. Okay, and in this case it is Z4 is that side, Z3 is this side. This is my Z3, Z4 is here, Z5 is that side, and Z6 is back this side again. In terms of the x-axis, we have seen that Z2 and Z1 are intersecting, so x0, x1, x2 are outward from the plane containing the Z1, Z2. x3 is this side, x3 is this side, x4, x5 and x6 are in that direction. Okay, so we have made our DH parameter table, which is like this. Now on the DH parameter, from the DH parameter table, we make our transformation matrices T0 to 1, the other way around, 0 to 1, 1 to 2, 2 to 3, and 3 to 4, 4 to 5, and T5 to 6. Okay, once we have made that, we find the individual transformation matrices, and then we multiply them out. Now I had mentioned in the last class that when we multiply them out, we multiply in a particular sequence. Okay, now let me explain what is the need for this sequence. Okay, so the procedure for solving the inverse kinematics of the Puma robot. So here we have T01, T12, T23, T34, 4, 5, and 5, 6. So 6 of them. And here we have what is T0 to 6 desired. Okay. Now, it has been seen that if you multiply them all together, okay, multiply them all together in one shot, then what is going to happen is this is multiplying in all one shot. So T0 to 6 is this now. Okay, R11, R12, R13, and each of these R's are like this. Now it shows that the R's and the Px, Py, Pz, all terms contain sine and cos. Okay, and you cannot solve from this set of equations. So if I take left side and right side and equate, then we cannot solve. So this is not a solvable set of equations. Okay, because you see that all the terms, whether it's R or it's Px, Py, Pz, all the terms contain sine and cos terms. So if you equate left hand side and right hand side, desired and the obtained T0 to 6 matrix, you will not be able to solve. So however, Piper is the one who actually found out the solution. Okay, he's the one who actually found that if you multiply in a particular way, say for example, you multiply these two, and then you multiply this, and then this, and then this. So if you multiply T1 to 6, okay, then you get one term Py which does not have sine cos terms. Okay, so 1 to 6, when we are multiplying this out, if you remember, what we did is we first multiplied 4 to 6. That means I start multiplying from the right hand side. Okay, so let me write T0 to 6, T1 0 1, 1 2, 2 3, 3 4, 4 5, and 5 6. Then this we start multiplying from this side. Okay, so first we multiply 4 to 6, then I multiply 3 to 6. Okay, then I multiply 1 to 2, 1 to 3. So what we do get is 1 to 6. So see, it is 0, 1 to 6. This one does not contain theta 1. Okay, because theta 1 is contained in 0 to 1. Okay, so this theta 1 is contained in this matrix, and this matrix is not there. Okay, T0 to 1 is not there. And hence, if I just multiply 1 to 6, then I get this R and this Px, Py, Pz. And in this set of equations, there is one Py does not contain sine or cos terms. Okay, so what Piper is the first person who suggested this solution. What he did is basically he targeted this term. And how do you do that? So when we have a set of equations like this, I equate the left hand side and the right hand side. I get this 0 to 6, and this is on the right hand side. Now if I want to remove from this set of equations, if I want to remove theta 1, what do? I take T0 to 1, bring it on this side, so it becomes T0 to 1 inverse. Okay, so this is my T0 to 1 inverse. Okay, so from this equation, from this set of equations, if I want to remove this one, what do? I simply multiply this with the inverse of, so this one I multiply this with 0 to 1, so I multiply this by T0 to 1 inverse. That's what is being done here. So I get T1 to 6. Now in this equation 4.56, so this is my equation 4.56. So in this set of equations, what are we targeting? We are targeting that Py. Remember, Py was equal to D. It was equal to D3, right? So in this set of equations, equating the 2 4 element from both sides of 4.56. What is the 2 4 element? 2 and 4. This is 2. Okay, that's 2, and 4 is this side. So when I multiply the second row into the last column, then what we get is minus sine Px plus cos 1 Py. I get this is equal to D3. Okay, so there is only one variable. Please note I get only theta 1 here, and here there is no sine and cos. Okay, sine and cos is not there. So if you start the equation from here, only then this system of equation is solvable, otherwise it is not solvable. Okay, so if I straight away multiply 0 to 6, you cannot solve this system of equations. Okay, so this is what we mean by solvability also, and the procedure by which we can solve. Now this is one equation, one unknown, so we can make the substitution. Px is equal to rho into cos phi, and Py is equal to rho into sin phi, and then making the substitution we can solve for theta 1, and we get theta 1 equal to, theta 1 is equal to 8 and 2. This we are able to solve and get theta 1. So we are getting theta 1. Okay, next what do? Is we take that equation. Now theta 1 is 1. Now we get back to that equation. 4 5 6 is known. We equate both sides of 1 4 and 3 4. Okay, so 4 4.56, which was that equation? 4.56. So that equation is 4.56, this one. So we equate which terms? We equate the terms 1, 4 and 3, 4. So 1, 4, so 1, 4 is this one, 1 into this, and 2, 4 is the 2, 4 is this, 2 into 4 is that again. So we get two equations, 1, 4, 1, 4, equating left hand side and right hand side of 1, 4, and the other is 3, 4. Left hand side is equal to right hand side. We get two equations, which is which we are obtaining here. So this is one equation, that's another equation. Okay, now here what are the variables? Theta 1 is known. Now we have theta 2 and we have theta 3. Okay, now you also note that there is a cos and a sine term there, cos 2 3, sine 2 3. So whenever sine and cos are there, then what we can do is we can square and add. So squaring these equations and adding, we get this equation, and what we do is theta 2 gets eliminated and we only have theta 3. So we are able to solve for theta 3. Okay, so we are able to solve for theta 3. So we have found theta 1 and theta 3. Okay. Next is if you consider 4.54, again we can now rewrite so that all the left hand side is a function only of theta 2. So what I can do is I remove t0 to 0 to 3, make it inverse and bring it on this side. Okay, so what happens is theta 1 and theta 2 are theta 1 and theta 2, it becomes a function of theta 1 and theta 2. Okay, then what we do is equating both sides of 1 4 element and 2 4 elements from the two sides of 470, this one. So 2 1 4 element, this is 1 and 4. Okay, and the other is 2 and 4. 2 and 4 is this one. We get two equations. Now these two equations have what variables? Theta 1, theta 2, theta 3. This is known, this is known. Theta 2 is not known. Okay, now these two equations, two unknowns, we can solve them simultaneously this way and get what is theta 2. Okay, so we are able to find theta 2. So we have found theta 1, we have found theta 2, and we have found theta 3. Now if you consider this equation again, 4.54, what happens if I take 0 4 on the left hand side? Okay, then what would happen is it has theta 1, theta 2, theta 3 and theta 4. These three are known now, so this is only one unknown. So what I can do is multiply with this, okay, and equating both 1 3 elements and 2 3 elements from two sides of 4.77 from this equation, which is this. What we get is two equations again. Okay, so from here I can get theta 5 and theta 6. Okay, so from here we get theta 5 and we get theta 6. Okay, so we have found theta 1 to theta 6. Okay, so we are able to find in the case of the Puma robot, we are able to find theta 1 to theta 6, and the solution procedure is given here. That what we have to do, we have to it has been found that if you start from here, look at the py element, okay, then only we are able to solve, otherwise we are not able to solve. So this is an example where there is a systematic way for solving the manipulator kinematics problem, without which we will not be able to solve the inverse kinematics of this manipulator. Now I explained about forward kinematics, I explained about inverse kinematics, we also looked at the inverse kinematics of the Puma robot. Now the question comes, how many solutions are there in this manipulator system? Okay, that would depend on where you are in your dexterous workspace or in your reachable workspace. So the workspace of this manipulator would be, outer workspace would be a circle or a sphere. Okay, so on the outer there are going to be single solutions near the, whereas in the center of it you could have large number of solutions. Okay, so depending on where you are your position and orientation is desired of the end effector, depending on that you'll have a number of solutions. So the number of solutions will keep changing in space, and depending on where you are in the workspace, you'll be getting a particular kind of solution. Yeah, so what we discussed today is the inverse kinematics, general inverse kinematic solution for the 3-link manipulator, which was a planar manipulator, probably the simplest example with theta 1, theta 2 and theta 3. Then we looked at the Puma robot, which is a little bit more complex, which has 6 degrees of freedom, 6 revolute joints. And we saw that you can solve it in a particular way if you start systematically solving from the matrix of 116 T16 matrix only. Okay, now it's very interesting and very important to understand why this solution is possible. Okay, now if you go back and try to understand and analyze that, why did it happen like that? Okay, now it happened like that essentially because let me go back to the this is something very important, so I'll just go back and try and explain, or maybe I'll do it in the next class. So what this basically says that why did the matrix 1 to 6 in the term Py only have D? Okay, did not have a sine and a cos term. Okay, so please think about it. I will discuss it in the next class and then we'll move on further. So we end here today. Thank you.